Okay, Assalamualaikum and good morning, everyone.
Waalaikumsalam, morning sir.
Waalaikumsalam, sir.
Okay,
Waalaikumsalam, sir.
perempuan tapi suara lelaki. Okay, so today we will continue with our lectures. Last week and last Monday, we have learned about the transfer function of translational mechanical system, which involves the movement of something, either forward or backward or upward and downwards, meaning that vertical or horizontal. So today we will look at another type of motion, which involves rotational motion, and how we can derive the transfer function of rotational motion. Okay, so after completing this lecture, you guys will be able to create transfer function for rotational mechanical system without gearing and also with gearing. Okay, so let's look at some basic elements in mechanical system. So in translational motion, we have spring and dampers, as what we have seen last week. And for rotational motion, we have also some similar things with linear motion. But usually for rotational motion, we have connections between different rotations through belting, okay? Or maybe through gears as well. So here we have belting. And for spring, we have a linear spring. So this is an example of linear spring. And we also have rotational spring. So the most common example of rotational spring is maybe you can find it in split kain, okay? Bag. Split kain. And damper, we have damper. This is the normal damper that you can find for a door. Okay? Maybe selalu jumpa dekat pintu lecture hall. Okay? Lama tak pergi lecture hall. Tiba. Okay, and for rotational damper, I never seen this before. So maybe for those who maybe yang pernah jumpa, mungkin familiar lah. Okay, so we use similar modeling steps as translational motion, which is the 4 steps. So first we decide on the input and output, and then we list the forces. But in this case, the rotational forces. And then we convert the forces into frequency domain, okay, and write the equation of motion. And then we isolate the input from output to find the transfer function. And we also have similar elements for rotational motion. We have spring, damper, and the inertia. Okay, for inertia, instead of mass, we have inertia J, okay, symbol J. So for spring, the same thing. We have the torque equals K times the rotational displacement. Okay, so instead of linear displacement, we multiply with rotational displacement, K theta. So in frequency, it becomes K. So similar with viscous damper, it's D times d theta dt, or linear rotational velocity or angular velocity. In frequency, it becomes d times s big theta. Okay. And for inertia, similar to linear motion, we have J times angular acceleration or rotational acceleration, e squared theta dt. And in frequency, it becomes Js squared. Okay, so same thing. It's analog, okay? Analogous to translational motion. The only difference is it measures rotational, but in linear motion, it measures the linear displacement. Okay, so let's look at an example of rotational system. without gearing. Okay, so let's look at without gearing. So now we have three rotational shaft J1, J2, and J3 connected with each other by dampers and spring. So similar to translational motion, if you hold, let's say hold J1, if you hold J1, then this section will become like a wall. So we have J2 and J3 that can move independently of J1. Okay, so to determine the degree of freedom, similar to linear motion. So in this case, we have three different masses. And here already indicates the three different displacement to measure. So meaning that the system has 3 degree of freedom. Okay, so we look at step number 1, which is to define the input and output. So the input is always the external force. So here it's the external torque T, and the output variable, so any of the angular position. So maybe theta 1 if you want to measure theta 1, or theta 2, or theta 3. Depends on what question wants. Okay. And step 2 and 3 is drawing the free body diagram and writing the equation of motion. So let's look at body J1 first. So on J1, we have damper D1 and spring K connected with J1. And this torque here, it is applied before spring. So meaning that it's applied on J1. Okay. So we draw the free body diagram J1, a circle, and then we decide the direction of theta 1. So in this case, we decided to be clockwise. So all the forces from the damper and spring will be against the motion of theta 1. So we have the inertia J1 theta 1 double dot in anti-clockwise direction. D1 theta 1 dot from the damper, also anti-clockwise, and K theta 1 also anti-clockwise. And then the spring here also connected with J2. So we have the effect of theta 2 from spring. So here T is clockwise. If you look at the direction given in figure, it's the same with theta 1. So T clockwise. And then the spring, the effect of spring from theta 2. So we have K theta 2. Sorry for the small k here. So theta K theta 2 will be clockwise, okay, because it's from theta 2. And then we get this free body diagram. Then we can write the equation of motion. Okay, so we can write the equation of motion, and later on maybe you can convert this into frequency. Okay, let's look at body J2. Okay, so similar with J1, the direction of theta 2 is clockwise. And on J2, we have spring and damper D2 connected with J2. So we have J2 theta 2 double dot, which is the inertia. And then D2 theta 2 dot from the damper, and spring K theta 2. And then the spring is connected with J1. And D2, the damper, is connected with J3. So we have two forces acting clockwise, effect from theta 1 and theta 3. So D2 theta 3 dot, because damper is connected with J3, and K theta 1 because the spring is also connected with J1. You check whether all the forces are there, then you can write the equation of motions. Lastly, we look at J3, body J3. So on J3, we have two dampers, D2 and D3. And then D3 is connected with the wall, so there is no rotational torque that is on clockwise direction. but D2 here is connected with theta 2. So we have the effect from theta 2. So we add D2 theta 2 dot. So everything is there, then we can write the equation of motions. Then we have now we have three equation of motions. Then you can write them and then convert it into frequency domain. Okay, so this is from the previous slides and converted into frequency domain. So put them in matrix form. So here you need to arrange. Okay, so start with theta 1 and then theta 2 and lastly theta 3. Okay, so always start with theta 1 equation. Okay, so the equation should be having a symmetry. Okay, symmetry about the diagonal elements here, diagonal lines here. So negative k similar to negative k, okay, like a reflection. Okay, and then 0 also equals 0 here, and negative s d2 here also negative s d2. There is one student that asked me whether this arrangement is important. Like if you write the first equation on second line, for example, the first equation on the third line. Actually, to be honest, to calculate the determinant, it's not really important pun. Okay, not really important about the arrangement. Whether the top row can be put downwards and so on. But to write the equation in matrix form, it's important to have the equation in the right location. But to calculate the determinant, it's fine. The location is fine, can be put anywhere as far as I concerned lah. Okay, it should be correct. Okay. Okay, so this is the equation. Then if you want to find theta 3, for example, then use Cramer's rule. Replace the third column with the output column here. Okay. Find the determinant divided by determinant of the original matrix. Okay, so it's better if you can simplify the top determinant to get theta 3 over t. Okay, so the bottom determinant, it should be okay if you don't simplify this. Sebab proses dia panjang, saya pun tak ingat. Okay, so better to get theta 3 over t as final answer. Maybe satu markah. Okay, so maybe tak dapat jawapan last ni, hilang satu markah, tak apalah. So kalau rasa confident jawab macam ni, okay je. Okay, so that's it for rotational motion without gears. So it should be similar to linear motion. Cumanya dia torque. Okay, so the difference is it uses torque. Okay, so now let's look at rotational system with gears. Okay, any question about the previous topic? Jangan malu-malu tanya. Okay, mungkin saya laju. Okay, so let's move on to rotational system with gears. So firstly, let's look at what is gear. So gear is a tooth machine part. So machine part with tooth, okay? Such as wheel or cylinder that is meshed with another tooth part to transmit motion or to change speed or direction. So we have rotational gears. We have gears connected with a straight gears. Okay, apa tak nama ni? I forgot already. And we have gears that is in this form. Okay, so this is bevel gear. I think you learn gears in mechanical design. Okay, the best subject in UMP. Okay, let's look at some properties of gears. Okay, so the two gears will turn in opposite direction. So if one gear, let's say gear A, turn clockwise, then the gear connected to it, let's say gear B, will turn the other way around. Okay, will be counterclockwise or anti-clockwise. But if the two gears are connected on the same shaft or on the same axis, like for example gear B and gear C, so they will rotate in the same direction. Okay, so when two gears connected with each other, so one rotate clockwise, the other will be rotated counterclockwise. Okay, so two gears revolve at different speeds depending on the number of teeth. Okay, so let's say gear A has many teeth, then the rotation will be slower. Okay, forgot already. Will be slower compared to gear B. Okay, let's look at about this speed and teeth on the next slide. Okay, so gear can convert torque to velocity, meaning that you can either speed up a rotation by using gears. So the common example is in your car. Okay? So if you use lower gear, like gear 1, your car will move slowly, okay? Slower. But the torque is higher for gear number 1. So usually you will use gear 1 to climb a hill, but the speed will be lower. So if you want to drive faster, you use gear 5, gear 5. But the torque is low, so you can use gear 5 to climb a hill. Okay. So the more velocity gain, the more torque is sacrificed. So if you use higher gear, you get more velocity, but you sacrifice the torque. So the ratio is exactly the same. So if you get 3 times original velocity, then you reduce torque by 3 times. Okay. So that's why in this example, the gear ratio is 3:1. So this conversion is symmetric. So we can also convert velocity to torque at the same ratio. So the price of the conversion is power loss. Okay, so there will be power loss due to frictions, but usually we will ignore about frictions. Okay. So in this example, the small gear has 80, and the bigger gear has 24. So the ratio is 24 divided by 8, 3:1. Okay. So if small gear turns 3 times, the bigger gear will turn only 1 time. Okay, so gear yang kecil ni lagi laju lah. So why we need gear? So a typical DC motor, so maybe you will learn DC motor in somewhere else, I don't know. So it usually operates at speed that is very high, okay? But the torques are very, very low. So we need to use gears to reduce the speed, or to use the speed of motor but at the lower speed. Okay, but the speed of motor is still the same, tapi kita reducekan speed tu untuk kegunaan kita. So we have gears connecting bertiga macam ni, and also ada 2 saja. Okay, so we will look later on. So about the gear ratio, so you can calculate the gear ratio by using the number of teeth of driver divided by follower. So to gear up, we increase velocity and decrease torque, and to gear down, we increase torque and reduce velocity. So in this case, let's say the smaller gear, if we identify smaller gear as the follower and the bigger gear as the driver, then the gear ratio is 24 divided by 8. But if you decide that smaller gear as the driver and the bigger gear as the follower, then gear ratio is 8 divided by 24. this one later on we will see how to decide which one is driver, which one is follower. Okay. And then the gear ratio equals number of teeth of driver divided by teeth of follower, or torque in, torque driver divided by torque follower, or speed follower divided by speed driver. So this formula is important. So please take note, okay, about this formula. Okay, so let's look at mathematical modeling of gear trains. So gear increase or reduce velocity. So energy of driving gears equals to the energy of the following gear. So to calculate the energy, we use the number of teeth times the angular displacement. So N1 theta 1 equals N2 theta 2 of the following gears. Okay, so let's say we have these two gears R1 with radius R1 and radius R2. So the distance traveled by gear 1 must equal the distance traveled by gear 2. Okay, the circumference distance. Okay, so you don't need to memorize the derivation. So the derivation is just to show you about the gear ratio just now. Okay, how we obtain the formula. So S1, the circumference of gear 1 equals circumference of gear 2. So circumference equals R1 theta 1 equals R2 theta 2, and you rearrange. And then the ratio of radius between gear 1 and gear 2 is equal to the number of teeth between gear 1 and gear 2. Okay, this is from the previous slide. Okay, the N1 times theta 1 equals N2 times theta 2. Okay, so this is the first formula relating angular displacement with teeth. Okay, so this is important formula. Okay, N1 over N2 equals theta 2 over theta 1. Okay. Okay, so you don't need to know about the radius. Okay, usually we don't deal with radius. And then we can also use the formula to relate the torque. Okay, so the work equals T torque 1, T1 theta 1 equals T2 theta 2. And then from the previous result, so here now from the above equation, so you rearrange, and then from previous result we get another relationship here. Okay, so the two formula here important. Okay, sama je formula macam tadi. Okay, so inilah the ultimate formula dia untuk gears. Okay, so please remember T1, T2, theta 2, theta 1. Okay, kadang saya pun tak ingat. Okay, so let's look at an example how we can apply gear into a rotational system and find the transfer function. Okay, so let's say we have a shaft here, and then we have another shaft with gear N1, and the shaft J with gear N2. So the two gears are connected. Okay, so dalam subject ni, in this subject, we will represent gear most of the time with these lines here, and we put N1 represent the teeth. We use N, okay, represent the teeth. Okay, so the torque is located on N1, torque T1, and we have theta 1 represent the gear 1 rotation or displacement, and theta 2 is the displacement of the shaft number 2, N2. So let's say if you try to hold this shaft J. When you hold shaft J, then the gear N2 cannot move, okay? Because shaft J is fixed already. So when N2 not moving and it is connected with N1, then N1 also will not move because it is connected by the teeth. Okay, so when N2 is not moving, cannot move, then N1 also automatically cannot move. So meaning that here there is only 1 degree of freedom only, even though there is 2 theta, theta 1 and theta 2. But actually the 2 thetas measure for different gears rotation. Okay, but there is only 1 motion involved in this system. Okay, so fixing J will fix the whole system. So 1 degree of freedom only. So we can use the similar modeling steps as without gears. Okay, so step 1, we decide on the input. So the input will be the torque, and the output can be theta 1 or theta 2, depending on what you want to measure. Okay, which we can convert this later using the formula that I said just now, that I said very important, the gear ratio formula. Okay, so step 2 and 3 is about the free body diagram and equation of motion. Okay, so firstly we need to transfer the torque T1 and theta 1, the angular displacement, into the second section here, meaning that we move these two onto the second section by using the gear ratio formula. So let's say we define a torque here. Let's say torque T2, for example. Sorry, T2. Okay, so to get T2, so we use the relationship just now, okay? The gear ratio formula. So T2 equals N2 over N1 times T1. So that's why you have this. Okay, so T1 times N2 over N1 is T2, okay? The torque on the shaft J. Okay, so when you bring theta 1 over to the other side, so you get T2, okay? Theta 2. Okay, so you don't bring theta 1 lah, because it's basically the same rotation, but the direction is different with ratio, okay? So we only bring the torque, but we need to convert the torque with the gear ratio. And then when you bring the torque here, now the system has no more gears. Okay, the gear dah hilang lah, dah reduce, dah boleh buang. Now the system becomes a normal rotational system without gears. Now we can draw the free body diagram. So theta 2 is counterclockwise. And then we have the torque, the inertia J, and the damper and spring. Okay, so 3 forces here, the 3 torque here will act clockwise against theta 2 direction. And then we add the torque T2, or this one, T1 times N2 over N1. Okay, so the direction is the same with theta 2. Okay, so this is the free body diagram of the system. Then you can write the equation of motion and write in terms of frequency domain. Okay, so this is the equation just now. Then if you want to find theta 2 over T1, then you just rearrange the equation. So you can use the gearing relationship. So just now we find theta 2. What happens if we want to find theta 1? So you use the gear relationship. So this is theta 2, the original equation. So you convert theta 2 in terms of theta 1 using the gear ratio formula. And then rearrange to get theta 1 over T1. Okay, so theta 1 over T1. So you get a slightly different transfer function. Okay. Okay, so this is the transfer function of theta 1. So when you find the transfer function of theta 1, if you compare to transfer function of theta 2, so here in theta 2, we have the ratio here. Bukan. Merepek ni. Aduh. Okay, so here we have the transfer function for theta 1, but all the inertia, J, damper, and K has a coefficient depending on the gear ratio, N1 over N2. And then it is squared, okay? So here we said that the gearing system causes some impedance transfer. So what is impedance transfer? So in this example, in this equation, we define the impedance transfer as the K destination equals the K source times or multiplied by the N number of teeth of the gear at the destination divided by number of gear of the number of teeth of the gear at the source. Okay, so what is destination and source? Okay, just now we move the T1 onto the second part here. So from the first part into the second part. So in this case, the sorry, pening sikit. Okay, so the second part should be the destination, and the first part should be the source. Okay. Later on, we will see how to decide on the source and destination. Mungkin slide ni dia pening sikit. Siapa lah buat slide ni? Okay, so if you want to find theta 1, so we decide to find theta 1, for example. So theta 1 is at the destination. Okay? Meaning that destination is the place where the variable that we want to find is located. Okay. So in this case, theta 1, we want to find theta 1. So we decide theta 1 on the destination. So K is the source. So we bring K on the other side, multiply by the gear ratio. So the N destination will be the N on the shaft with theta 1. And then the N source will be the N on the shaft with K, or with the things that you want to transfer. Okay. So that's why you get K from the source and then multiply by gear ratio squared. Okay, so there's a square here. So similar to damper, so we transfer it to theta 1, so it becomes the source, and theta 1 is the destination. So to find the impedance, the new impedance, so you just multiply D with the gear ratio and destination over N source squared. And lastly, similar to J, okay, the inertia J. Okay, so maybe a bit confused. Let's look at an example how to perform impedance transfer using this concept here. Okay, so this is another example. Okay, now we have both sides of the gears. We have the J1 and damper, and the other side also we have J2 and damper, but the other side we have extra K spring. So example just now, we don't have this J1 and D1. We only have the torque and the displacement. So now we have two things here, two extra things, damper and J. So let's say if you want to find a trans function theta 1 over T1, for example, okay? So how to do this? So here, given theta 2 over T1, okay, so we need to do something here. We need to do the impedance transfer. Okay, so because theta 2 is located on this part, while T1 is located here, so I think it's better if you can bring T1 onto this side, okay? So now meaning that theta 2 becomes the destination because we want to find theta 2 over T1, okay? So we make everything on theta 2 as the destination, okay? So everything not on theta 2 becomes the source. So we bring everything from the source using impedance transfer into the shaft number 2, the destination. So how to do that? Okay, so firstly, let's look at the damper. So on the source, we have damper D1, and on the destination, we have damper D2. So I said just now, we bring everything from source to the destination, okay? Meaning that everything on the destination becomes fixed, okay? We don't do any impedance transfer. So we only do impedance transfer on everything on the source, okay? So we bring D1 to D2. So we calculate the effective damping. So DE equals D2. So we don't do anything on D2 because it's already on destination. Plus D1 because D1 is on the source and we want to bring it on the destination. We multiply by the gear ratio. So N destination, this is N source squared. So N destination is the N2 and N source is N1. So N2 divided by N1 squared. Okay, so we find a new equivalent damping. Now we find the equivalent inertia, J. So similar to D1, we bring inertia J1 onto the destination, the shaft number 2, because we fix shaft number 2 as the destination. So we calculate the equivalent J. So equivalent J equals J2. So we don't do anything on J2 because it's already on the destination. Plus J1 times N destination over N source squared. Okay. So that's how you do impedance transfer. So you do impedance transfer from source to the destination. So in this case, the impedance are the damper and also the inertia J. And lastly, on the source, we don't have spring, so no spring, but on the destination, we have spring K2. So we still need to find the equivalent spring, equivalent K. So the equivalent K will only equals K2. We don't have K1 because here on the source, there is no K1. So you don't need to do impedance transfer for spring. Okay, so K equivalent only equals K2. Then from the system, just now we calculate all the equivalent damper, equivalent inertia, and spring. Now we can redraw, okay, redraw the system into a single degree of freedom system with new damper J and K. So here the new damper is DE, new J is JE, and new K is KE. And we also transfer the torque. So here we calculate T2. So T2 equals T1 times N2 over N1. So here we don't square because this use the formula, gear ratio formula, okay? The square is the formula for impedance transfer only. Now from this diagram, the new diagram that we redraw, then we find or we draw the free body diagram. Okay, similar to the previous example, because it's 1 degree of freedom only. Okay, you determine the forces or the torque, and you can write the equation of motion. Write it in terms of frequency. So here it's in theta 2. Then you convert JE, DE, KE with the actual formula, this one. Substitute, and you get the final equation here. Now you need to rearrange to find theta 2 over T1. Okay, just rearrange the equation. And you can also find theta 1 over T1 by using the gear ratio formula. Okay, so the gear ratio formula is T1 over T2 equals N1 over N2 equals theta 2 over theta 1. Okay, so this formula is important, and also the impedance transfer formula. So the impedance transfer only apply on the damper, the inertia J, and the spring K. And the gear ratio formula is only on the torque, number of teeth, and also the displacement. Okay, so don't confuse, okay? Okay, so this is about gearing. Any question? Ke tengah makan ke apa ke?
No question.
Saya tak tahu. Kalau
Okay.
yang nak main information dengan source tu, dia dengan soalan ya?
Oh tak. Okay, yang tu menarik. Nanti kita akan tengok dalam tutorial yang keempat. More example about deciding source and destination. Usually, like in this example, let's say in the question wants theta 2 over T1. So we can use T2 as the destination and everything else as the source. But sometimes there are cases kita nak T2, theta 2, but we cannot use theta 2 as the destination, because to use theta 2 as destination, it will make the equation more complicated. Yang tu nanti kita akan tengok dalam tutorial. Okay? So tak muat letak dalam slide, nanti jadi panjang sampai 2 jam, tu student dah belah dah. Okay, so for now, I want you to understand how to perform impedance transfer, how to perform the gear ratio conversion, and then maybe try some tutorials. Kalau ada stuck, later on we will discuss about tutorial. Okay. Okay. Let's see. Okay. Okay. So we will look at this example during the tutorial next week. Okay. Because this will be suitable if we discuss this together with tutorial. So any question before we end our lecture?
No, sir.
Agak pening juga sah. Ambil masa sikit.
So memang pening. So that's why I remind you to familiarize about the linear translation motion, because the translational motion is macam easier sikit dari rotational motion. But once you understand translational motion and you understand the the rotational motion without gears, then it will be a lot simpler to understand about gears. Okay, sebenarnya gear diorang kata lebih senang. Bagi saya gear susah. Tak tahu kenapa diorang kata gears. So, part 1 boleh start. Yes. Okay, thank you for the reminder. So, for project, you can start part 1 because part 1 is about lecture number 1. Okay. So, I would like to ask you to start early because the due date for project 1, 10%, is the end of week 7. I think I said Saturday midnight kot, lupa dah. So, please start early so that tak adalah hari Jumaat week 7 tu baru banyaknya projek. Tak naklah belajar dengan lecturer ni. Teruk tiba. Okay, so please start early. And then part 2 and part 3 will involve chapter 3. Okay. So maybe next week kita akan masuk chapter 3. Next week, week 4 already sempat. Okay. Chapter 3 ada 3 topik. So banyak jugalah. So we will discuss the tutorial for rotational gears, more example. Okay, any more question?
Sir,
Saya
nak tanya saya.
Ya, boleh.
Ni pasal midterm.
Midterm tak ada.
Sekejap. Ada.
So kita ada midterm, kita tukar
Kita
midterm dengan quiz dan project.
Oh.
So quiz kita untuk markah midterm. So quiz kita akan ada quiz 1, quiz 2, quiz 3. So quiz 2 rasanya akan release next week. Okay. So I will put an announcement in column. And project 1, which consists of part 1, part 2 and part 3, 10% for midterm. So overall there will be 12% from quizzes, 10% from project 1. Okay, so 22% for midterm. So there will be no midterm test like last semester, like previous semesters.
Okay, sir.
Okay. Okay, sebab korang punya subjek ni dah jadi 60% final. So tambah test lagi nanti 80% final. Tak naklah main banyak exam. Nak menanda penat. Kita buat mudahkan bagi projek. Okay, any more question? Okay, so if you don't have any question and if you like to ask me anything, just ask through WhatsApp, okay? And that's it for today's lecture. We will continue next week, Monday, on tutorial 4, rotational motion. Please try. If you don't know how to do it, boleh try sampai mana yang faham lah, okay? We will discuss more about the tutorial next week. So that's it for today's lecture. Thank you. Assalamualaikum. Goodbye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.